Hello, everybody. My name is Clayton Strawn. It is a great honor to join the ARCS Foundation today to describe my research work. I'm a fifth-year grad student in physics at UCSC, and I study galaxy formation and evolution. My main contribution has been to developing post-processing software for analyzing cosmological galaxy simulations. To that end, I've created 3 new analysis packages in Python to do different kinds of analysis, made several contributions of my own to the larger open-source simulation analysis community. I've also been proud to expand this opportunity to a new generation of scientists, including having contributions from now 7 local high schoolers through the UCSC Science Internship Program. So today I'm going to talk about the main results of my research so far. My focus has always been on the circumgalactic medium, or CGM, which is the region of gas outside of galaxies proper, but inside their dark matter halo. This region is very low density and difficult to see through either direct or indirect forms, but the massive volume that it fills means it contains, in most cases, even more gas than galaxies themselves. We need to understand this region to understand, among other things, how gas flows into and out of galaxies. We know it has to flow in because otherwise galaxies would run out of material to form stars. We also know it has to flow out because space is full of metals, and those are only created through stellar fusion reactions. But actually seeing this at large scales is a challenge because observations are often extremely indirect. The most common observational data is what we call an absorption line, which is where we look at a bright object behind the CGM, use the features of the quantum spectra to infer that certain absorbers are found along the line of sight. The most important absorber for our purposes is metal ions. In astronomy, metal is anything bigger than helium, specifically oxygen-6, or 5 times ionized oxygen. What I focused on is studying the way this ion tends to arise in the CGM in simulations in order to help characterize the results that come from fairly sparse and complex observational signatures. There are basically 2 ways to ionize a particle. On the one hand, it can have high-speed collisions with other particles, sometimes knocking off an electron. It's called collisional ionization. On the other hand, it can get ionized by a high-energy photon, which permeates all space at some energy density. This is called photoionization. Whichever one we assume created the ions we actually see will affect how we interpret the observational data. Because photoionization happens at relatively low temperatures, and collisional ionization happens at fairly high temperatures. In the simulations I've analyzed, we've seen that oxygen-6 actually rises from both sources in the CGM, meaning that to some extent, everybody's right. But they don't arise in the same places. Photoionized oxygen-6 is primarily found in inflowing cool streams, and collisionally ionized oxygen-6 is found in the thin interface layers on those streams, which are nearby but not in exactly the same place and have different turbulent properties. What we want to do next is free this analysis from this specific simulation, which has its own unique quirks and idiosyncrasies, to see if the structure is universal in analytic models or in other simulations. There's a lot of fascinating new data coming online, so understanding this structure will help us interpret the results we get out of the real universe. Thanks again for your time and for the ARCS Foundation for this opportunity.